Hello, this session is the third exercise of the hydrology video tutorial. In the first exercise, we developed a hydrological model using the soil moisture method. We added catchments and their runoff infiltration links manually. The areas and climate data for each catchment were entered manually as well. In this exercise, we will use the catchment delineation mode in WEAP. The development of a hydrological model in WEAP can be done manually as in the exercise 1 or assisted as we will do in this exercise. There should be no difference in the results if the input data are the same. The difference is the format in which you need the data. You need to download the O8 hydrology folder to follow this exercise. We will work with the GIS version of the SEI catchment delineation mode tutorial model. The area is the Rocha River Basin located in Cochabamba, Bolivia. Before starting, it is important to understand what information is required and how WEAP will process and use it to assist you in developing a hydrological model. Using the catchment delineation mode requires input information in specific formats. The inputs needed are the digital elevation model, the catchment disaggregation, and the climate. The digital elevation model is used to delimit the catchments. The default DEM used by WEAP is the Hydrosheds product. There are two resolutions available, 500 meters and 90 meters. The DEM that WEAP uses cannot be changed. Other entry is the netcdf file to define the catchment disaggregation. By default, WEAP has the land cover product from the European Space Agency, which is available at a resolution of 300 meters for 2010. The resolution of the netcdf file to disaggregate the catchments must match the resolution of the DEM. The default climate data available in WEAP was processed by the Terrestrial Hydrology Group of Princeton University. The data have daily and monthly precipitation, temperature, and wind speed from 1948 to 2010 at a resolution of 28 kilometers. From any point of interest and considering the DEM, WEAP automatically delimits the basin and its main river. Then, WEAP makes the intersection between basins and the netcdf files, both catchment disaggregation and climate. Remember that the resolution available for the DEM is 90 and 500 meters, for land cover 300 meters, and climate 28 kilometers. It is very important to keep in mind the basin extension to be modeled and the resolution of the input information in WEAP. The resolution has effects on the calculation of the variables. Here we see an example of area estimation at three different resolutions. From the input information, WEAP automatically delimits basins, catchments, and adds rivers. Besides, it automatically creates the structure in the data view considering the defined disaggregation. Here we see an example of three basins added using the catchment delineation mode. WEAP automatically adds the area by disaggregation classes. Also, it estimates and assigns climate data to each catchment. If the default database is used, we will have precipitation, temperature, and wind speed. The subdivision by elevation bands is created for each catchment, and the disaggregation classes are also created. in this case considering the default data by land cover classes. The following 4 slides summarize the most important points to consider when using the catchment delineation mode in WEAP. You can pause the video to read them carefully. As we progress in the exercise, we will address these points. Go to WEAP. As I mentioned, we will work on the GIS version of the SEI Catchment Delineation Mode tutorial model. Go to Area, revert to Version, and select the GIS version. The area is the Rocha River Basin located in Cochabamba, Bolivia. During the exercise 1, we manually added catchments, but WEAP can assist this process by using the catchment delineation mode. We are going to use our own disaggregation and climate netcdf files. In the Exercise 3 folder, we have the climate and land cover geomorphology netcdf files. The first one contains climate and the other one the catchment disaggregation by land cover geomorphology classes. The CSV file land cover geomorphology contains the class names of the catchment disaggregation values of the netcdf file. The catchment disaggregation classes correspond to the combination of the land cover and geomorphology classes. Check the Excel file land cover geomorphology. To start using the catchment delineation mode, the area boundaries need to be defined first, as these can determine the extent of the basins that WEAP will create. The more detailed the area is, the faster the basins will be added and less information will be downloaded. To access the catchment delineation mode, we have two options. Going to Schematic Catchment Delineation Mode at the top, or right-click on the schematic and select Catchment Delineation Mode. A panel on the right appears in the schematic view. As you move the mouse over the schematic, you will see information in the DEM box. We can use 3 input data. The digital elevation model is mandatory. We must select the resolution to be used. The catchment disaggregation and the climate data in netcdf format are optional. First, we define the resolution of the digital elevation model to be used, 3 or 15 arc-second. WEAP may not be able to use the 90 meters data on very large basins due to memory constraints. If WEAP tries and fails at the higher resolution, try again with the lower resolution. Then we must decide if the elevation bands will be created. We will create elevation bands every 1,000 meters. Next, we define if a disaggregation for the catchments will be created. In that case, the netcdf file must be selected. Below the Select button, we see the data name that is being used. It is the land cover data from the European Space Agency. This option allows you to include the disaggregation classes even if their area is 0. Including area equals 0 ensures that each catchment has all the disaggregation classes in the data tree. Finally, we define if the climate data will be added. By default, the data being used is from Princeton University. This information is available daily or monthly from 1948 to 2010 with a resolution of 0.25 degrees. In this slider, we define the location of the runoff inflow node, closer to the head flow or at the tail flow. I prefer tail flow. The importance of the node inflow location was explained in Hydrology Exercise 1, Developing a Hydrological Model in WEAP video tutorial. The catchment disaggregation file has categories. The default file has 22 categories, but we can group them as it is needed. WEAP groups them into 9. We can create, delete, or rename the categories. This can also be done by modifying the area.ini file of the model. We will see how later. If you want to use your own netcdf file, select the Create New Land Cover Data Source option. We need to assign a name. Type Land Cover Geomorphology. Click on this button to select the file. Go to the Exercise3 folder and copy the netcdf files, Climate and Land Cover Geomorphology, and the CSV file, Land Cover Geomorphology. Paste them here. Make sure that you are in the folder of the model, SEI Catchment Delineation Mode Tutorial. You will not see the CSV file because only the netcdf files are shown here. Select the Land Cover Geomorphology file. Open. The file has only one layer, and it has 106 classes. Delete all the categories. Click on the Import option and select the Land Cover Geomorphology file. 106 categories imported. OK. We have included our disaggregation file, and we will use it to create the structure in the data tree. WEAP has these 9 categories by default, but we want to use the 106 categories. Doing that here is time-consuming. That is why it is better to do it by modifying the area.ini file. The ini file must be modified when the model is not active. In order to do that, we need to close WEAP. Before closing, save the changes we have made so far. Go to Area, Save, and then close WEAP. Open the Excel file Land Cover Geomorphology. Now open the area.ini file of the model. Go to the WEAP Areas SEI Catchment Delineation Mode Tutorial folder. Open it with a text editor. The catchment disaggregation contains 9 land cover classes and 14 geomorphology classes, 126 classes in total. Here is the list of the classes. Once the land cover and geomorphology data were processed in a geographic information system and saved in a netcdf format, 106 classes were obtained in total. In the area.ini file, you see the structure used by WEAP to read the catchment disaggregation files in netcdf format. Here is the ESA file structure. This is the structure for the netcdf file we added, Land Cover Geomorphology. First, you define the original class values and assign their names. Then, you define the categories to group those classes. Finally, you assign the categories to the original values. You need to use this structure. The structure was created for both netcdf files. We can build the same structure in Excel. Then copy and paste it to the area.ini file. WEAP will load that information when it opens again. We manually added the netcdf file and named it land cover geomorphology. Now we will add these lines to include the same file but with another name. We will name it new land cover geomorphology. Copy these yellow lines and paste them at the end in the area.ini file. Close the file, saving the changes. Reopen WEAP. We must open WEAP directly, not from the model file. Otherwise, the changes will be lost. Go back to the catchment delineation mode. Click on the Select button below the Create Land Cover Branches text. We can see that there are three options. The default ESA data, the one we added before closing, and the one we included by adding the yellow lines at the end of the area.ini file. The last two options correspond to the same file, but WEAP loads two different structures with a different name due to the lines we added in the area.ini file. The land cover geomorphology option has the classes grouped by the default WEAP categories. The new land cover geomorphology option does not group the original classes. We want to use the original classes of the catchment disaggregation file. Select the new land cover geomorphology option and click on OK. For climate data, by default, WEAP has monthly and daily data from Princeton University. There is also an option to specify your own netcdf file. Click on the Select button below the Load Climate Data text. Select the user-specific file netcdf format option. Select the climate file. Open. Depending on the name of the variables in the netcdf file, WEAP can automatically relay the variables in the file to the variables needed in the hydrological method in WEAP, in this case specifically the soil moisture method. These options are the same as the ones you see in the Read From File wizard window. The period and the resolution of the file are shown here. We have climate data from January 1980 to August 2016 with a resolution around 5.6 kilometers. I recommend that you carefully read the information available in the WEAP help about the catchment delineation mode. It describes the technical details that must be considered to use it correctly. Close this help window. Click on OK on the Select Climate window. Once we have finished setting up everything on this panel, we are ready to add catchments in the schematic. To add a catchment, left-click anywhere in the area. Left-click on this part to add the first catchment to the model. The first time we add a catchment, it will be associated with a basin. Name it Catch 1. In this case, this catchment will be Catch 1, but at the same time, it will represent a basin. Finish. The first time, we will add the largest basin found within the area boundaries. It may take a while. It depends on the area boundaries. If we want to add a new catchment within that basin, left-click again inside. After the first catchment is created, you will see 3 new GIS layers. Turn off all layers to see them one by one. Right-click on the panel and select Hide All Layers. The basins are delimited in red. The catchments are shown in diagonal fill style. The rivers are shown in light gray. You can increase the detail of rivers using this slider. We can see how the rivers can be shown in more or less detail. Set a medium detail. The modeling points and modeling rivers layers define the interest points and rivers. Reduce the size of element labels so they do not interfere visually. Go to Schematic, set WEAP node label size, and decrease the size. OK. We can modify the pour point of the catchment. We want the catchments from the points of interest. To modify the catchment, place the pointer over the pour point. The pointer will change from the arrow pointer to a double-headed cross arrow. Left-click and drag it to the new pour point on the river close to the yellow point. Modify the pour point until the catchment boundaries match with the basin boundaries layer. We can add catchments from the points of interest following the same process. Zoom in when necessary and left-click on each point. The basin should no longer be named because the new catchment is within an existing basin. Name the catchments considering the label of the points. For example, catch 2. To create a catchment at an exact point, hold down the Alt key when left-clicking. Hold down the Alt key and left-click on this point. Catch 3. Continue adding the rest of the catchments. Catch 4. Catch 5. Catch 6. Catch 7. And catch 8. We can modify the river within the catchment as well. Place the pointer over the headflow point. The pointer will change. As the point moves, WEAP identifies paths inside the catchment. We can move it here. Once we have finished creating the catchments, we can close the catchment delineation mode. Right-click and deselect the catchment delineation mode. It may take a while because WEAP will create the data structure and include area and climate information. Once WEAP finishes processing, the panel on the right will close. WEAP will download information in cell size 1 degree by 1 degree and store it in the Downloads folder in the WEAP Areas folder. The catchment delineation mode can be activated when you need it. In addition to the catchment representing the basin from the points of interest, we need to add the basins from the streamflow gauges. Add the catchment from the red point representing the streamflow station. Right-click, select Catchment Delineation Mode. Hold down the Alt key and left-click on the point. Name it Catch Taquina. Finish. Close the Catchment Delineation Mode. Right-click, deselect Catchment Delineation Mode. Each time a new catchment is added, the model is updated, and the structure is created for the new catchments. The first time takes longer because the information is downloaded according to the boundaries of the area. Add the streamflow gauge to the model. Drag the streamflow gauge from the element panel and drop it on the river downstream of the inflow node. Name it Taquina. We should have 8 rivers, 9 catchments, 9 runoff infiltration links, and 1 streamflow gauge. The catchments are added automatically at the center of the area that they represent. If the pour point is modified, the catchment location does not change. You can change its location, drag and drop if necessary. The rivers cannot be removed if they were added in the catchment delineation mode. If we try it, a warning will indicate that the river cannot be removed because it was added in the catchment delineation mode. To delete a catchment, you must access the catchment delineation mode. When you delete a catchment created in the catchment delineation mode, it will delete the river also, unless it has an inflow from other rivers or if the river also flows through another catchment. Remember that WEAP does not have the undo function. You can save the version if necessary. Right-click on the catchment and select Delete. WEAP displays a confirmation window. Select Yes. The catchment and the river are deleted. Add the catchment again and close the catchment delineation mode. Go to the data view and check the structure under each catchment. We have the elevation bands and then the disaggregation classes. The area is shown in hectares. The area unit can be modified. Go to General Units and then to the Land Use option. We can select the unit in the drop-down menu of the Land Area Unit option. Select square kilometers. To a change in units takes effect, you must reopen the catchment delineation mode and make any modification, such as adding a catchment or moving a pour point. Then close the mode. Go to the data view to explore the data tree. The unit will be updated. Under the demand sites and catchments are the created catchments. Under the supply and resources are the associated rivers. It is important to organize the data by assigning to the catchment and the river names that easily identify the elements. It also serves to represent the cartography and the hydrographical division in the study area. Each catchment created using the catchment delineation mode has a structure depending on the selected option and information. If you include elevation bands, the elevation bands will be displayed first. We use in this model elevation bands every 1,000 meters. If we included a catchment disaggregation, the classes will be under the elevation bands. The classification in this case is based on the classes of the land cover geomorphology file. The areas are entered at the lower level. We see that there are areas without information. That is because we selected including area equals 0. Regarding climate, precipitation and temperature were added based on the climate file that we used. The rest of the climate variables have no information because the netcdf file we used in the catchment delineation mode did not have the climate data. In this graph, the precipitation for the year 2015 is displayed. Remember that the period of the climate information is between 1980 and 2016, and it is monthly information. Go to General, Years and Time Steps, and change the time horizon. 1980 to 2016. Select 12 for the time steps per year. Now the current accounts year is 1980. If we go to the reference scenario, we can see the whole time series. For this specific example, the precipitation value in the netcdf file corresponds to the monthly precipitation divided by the number of days in every month. We need to multiply this data by the number of days of the month to obtain the monthly precipitation. Go back to current accounts. Export the expressions for the precipitation variable. Go to Edit, Export Expressions to Excel. Export the variable precipitation, all branches, current account scenario. It can take a while because each subclassification of each catchment has its own expressions. This process is required for this specific file. We can use the concatenate function. Type in the L4 cell, concatenate, open parentheses, select the expression cell, K4, comma, open quotation marks, multiplication sign, add the word days, close quotation marks, and close parentheses. With this change, WEAP will multiply each precipitation value by the days function. The days function is equal to the number of days in each time step. Because it is a monthly model, it will be equal to the number of days in each month. Apply the formula to the entire column. WEAP imports the expressions from the K column. Replace the expression. Copy the expressions created in the L column and paste them as values into the K column. In WEAP, go to Edit, Import Expressions from Excel. We see on the graph that the original monthly precipitation value in January is 4.6 millimeters. With the new expression, that value times the number of days, in this case 31, it should be around 142 millimeters. The monthly precipitation value for January is now around 142 millimeters. Once you have the catchments added, the model is ready to assign the hydrological parameters to each catchment and proceed to its calibration. Hydrological parameters must be added on these tabs, either manually or by links to key assumptions. In this case, we will manage the hydrological parameters by using key assumptions. There is no way to import and export structures of key assumptions between models. This is a process that must be done either manually or by scripting in each model in WEAP. From here, we must follow the same steps as in the exercise 1 to complete the hydrological model. First, we need to create the hydrological parameter structure as key assumptions. Then we can link the key assumptions to the hydrological parameters of each catchment. It is better to add all the catchment first and then linking the parameters. If you link the parameters and then add another catchment, you will need to repeat the process for the new catchments added. We will create the key assumptions by running the script. Go to Advanced, Scripting, Run, area scripts and select the script parameters. We will see that the structure starts displaying. This script is for this model only. You can modify it according to your interests. It can take a while. The Excel file key assumption helps to explain the structure. Each hydrological model requires a specific key assumption structure depending on the catchment disaggregation that you define. This time, the disaggregation is from the combination between land cover and geomorphology. We are using the soil moisture method. We will consider 9 hydrological parameters to calibrate the model. These 3 parameters are divided by the land cover geomorphology classes. These 2 parameters are divided by the geomorphology classes. These 4 parameters will be global. The structure and initial values are in the key assumptions sheet. You can explore it while the script finishes running. Besides creating the key assumption structure, the initial expressions were also assigned to each key assumption by the script. Once it finishes, we can check the structure created in WEAP. It should look like this. We have been making progress, and it is a good practice to have backups. Save the version before continuing. For example, my basins. The next step is to link the key assumption to the hydrological parameters and add the stream flow data to the gauge. If you have followed the hydrology video tutorials, you should be able to do it by yourself. For linking the key assumptions, we can exchange expressions with Excel. Go to Edit, Export Expressions to Excel. Export to New Workbook, Branches All, Scenarios, Current Accounts, Variables All. You need to link the key assumptions to these 9 parameters. You can use these expressions to complete the file, and then import the expressions to WEAP. In the parameters to WEAP sheet are all the expressions that should be assigned in the model, and you can use it to verify the file you are completing. For the tutorial purposes, there is a version saved after this process was made. Go to Area, Revert to Version, and select the complete hydrological model version. You can pause the video and check that the hydrological parameters are linked to the key assumptions. This version already has the streamflow gauge element and its observed streamflow. You can explore the results. There are favorite graphs already saved. The final step is to calibrate and validate the model. You can use the Excel file calibration.